Now inverse circular functions. Not every function is invertible. So what is the condition for a function to have the inverse? We know it should be a one-to-one function. Then what is a one-to-one function? Let's have a review of the definition of one-to-one function. If a function is one-to-one, that means whenever x1 is not equal to x2, then the function values f of x1 is not equal to f of x2. So that is a one-to-one function. That means this fact, it has to be true for any arbitrary values in the domain. Whenever x1 is not equal to x2, and the function values will not be the same. If this is true for all x1, x2 in the domain of the function f, then this is called a one-to-one. So, and we know this definition of one-to-one. We can also write in a different way. This definition is equivalent to another way of saying it would be whenever f of x1 is equal to f of x2, it's contrapositive, right? This implies x1 has to be equal to x2. You see, this statement, instead of using inequality, we use equality. Yeah, so that is when the two function values are equal, then the input values must be the same. x1 is equal to x2. So which one do you like? They are equivalent. So that is, if you compare this to this and this, these two are equivalent statements, right? This is the contrapositive of that other one. Now, with that definition, we are going to look at number of functions, and we will see which one is one-to-one through some examples. So this, okay, need to scroll down. Yeah, so based on the definition, we have this horizontal line test. Horizontal line test is to say for any horizontal line, if there is only at most one intersection with the plot of the function, then it satisfies the horizontal line test. So you see, I have two functions here. One is a linear function, which is this 2x, that, right? The function is y equals 2x. And the other function is x squared function, y equals x squared. So either y or f of x, that is our different functions. And you see that this first function satisfies horizontal line test, right? For any horizontal line you draw, and there is at most one intersection. Yeah, and with the curve. And the second function for any horizontal line, it's possible you have more than one intersection. So the second function does not meet the horizontal line test. It is not one-to-one, that means. And let's check using definition. If you use definition, let's see, for different axes, that is, no matter, yeah, whenever x right? Whenever you have a different x values, then their function values will be different. So you can see the y values will be different. This straight line is actually increasing function. So the larger the x, the larger the function value. So whenever the x values are different, the function values are different. So that's easy to see. And also using the alternative definition, then you can check whenever the function values are the same. So like if you choose this function value, this y value, which is 5, right? 5. If y is 5, so let's give any y. It doesn't have to be 5, any y, which is a constant. That's the horizontal line. So then there is, so whenever the y value is given, the x value is unique. So then you can find the x, which is a half of 5. So this x, that means whenever the y value is given, the x is uniquely determined. So if it's 1 to 1, then that means x can be solved uniquely given y. So if your y is given, then your x can be found, right? So you often write the function value as a y. So if that is the given function and we know it is 1 to 1, then for any given y, we can find a unique x. So this is a concrete example. So because it's 1 to 1, we can solve it for x. So this will be called the inverse function, because previously the y is found for each given x. Now x is found for each given y. So this is the inverse of the original function. So a reversed relationship. But let's look at this next function, which is not 1 to 1. So if this y equals x squared, this function, if you use the horizontal line test, you can see it's possible to find different x's, right? If you have x1, x2, although they're different and they have the same y value. Yeah, so as long as there's one such a case, then it's not 1 to 1. Because 1 to 1 function demands that for any x1, x2, whenever they are different, their function values should be different. But if you find one such a case that x1, for example, x2, they are different, but their function values, right, will be the same. And so that violates the 1 to 1. So it's not 1 to 1. And so if it's not 1 to 1, then by horizontal line test, you can easily also check using horizontal line test if there's at least one horizontal line that intersects with the graph of the function more than once. That shows for certain y, for example, if at this y, it intersects the curve more than once, that shows there will corresponding different axes, right? Such that this y value can be achieved at different axes. So that means although, yeah, that also tell the same thing. So that means, so this whenever the function values are equal, then the x1, x2 must be the same. That's the alternative definition of one-to-one. However, this violates that. So that means whenever the function value is the 4, and we hope the x1, x2 must be the same, right? If they are both equals 4. So that's the alternative definition for one-to-one, but this one, horizontal line test, shows that. So it's not one-to-one. If you still try to find the inverse, imagine if you have such a function and you try to find x, then the x will be two possibilities there. And it could be square root of y, right? Either positive or negative. So you can pick a specific case. So when y is 4, for example, then the x could be either -2 or +2. That means you cannot find the inverse that is still a function, because in order for this to be a function, each input should correspond to a unique output x. So this, if x has two possible values, then that cannot be a function. So we cannot invert this given square function, right? X square function, because if you try, you will get two possible x that is not a function for each y. So what we see that in order to find the inverse, we require the function to be one-to-one. Yeah, this is an example to show if it's not one-to-one, then you still try to find the x in terms of y. Suppose y is given, how do I get x back? Then the x is not unique, then that is not a function, right? Function requires a unique value for each input. Now we will look at this inverse. What is inverse? It is a pair, just like any function. If it's a function, right, you have a pair, input and the function value. That is the value if that belongs to f. This is a point, right? It is, if it belongs to this function f, that means this x is a possible input for f, and this y is a value at x. So this outer pair must be a point of graph of f. So when the function is invertible, then the input will be the suppose the y value, then you will get x back. So it's a reversed relationship, and then that's our definition for inverse. Definition for inverse is that when xy belongs to f, then the inverse is defined as this point, yx. And x has to be unique for each y value. That point will be on the graph of inverse. So what's the relationship? If we plot those points and compare it with this point, we know the x, y, yx will be symmetric, right? Just think of any point. So if you have a point A and B, and you try to plot B and A, and they're symmetric about the line y equals x. So if you draw the y equals x, this line, and suppose you have a point, if this is AB, which is on the graph of f, original function, and then BA will be on the graph of inverse of f. So you see the relationship AB and BA, they are symmetric about this line, y equals x. So that means we can anticipate the graph of inverse as long as we try to discover the reflection of f across the line y equals x. So here's a function. And if we have this function, it's a straight line. And by the way, there is a sufficient condition for a function to be one-to-one. That is, if a function is increasing or strictly decreasing, then it is one-to-one. That is a sufficient condition, easy to apply. But of course, there are other possibilities for a function to be one-to-one. So this sufficient condition means if it satisfies this condition, then it will be one-to-one. So in that case, we look at this line. It is an increasing line, right? It is definitely a one-to-one because different x will correspond to different y. Also meaning, yeah, larger the x, the larger the y value. So it's with a positive slope. Okay, so it is definitely a one-to-one, so we can find its inverse. Let's go ahead, find its inverse. That means I want to get x equals something given y. So by solving this equation for x, all we need to do is to, step by step, we eventually get x isolated from this expression. So here we add y, 1 both sides, right? So you get y plus 1 equals 3x. You add 1 both sides. So you change the equation into this. And now, after that, you can get x, right? If we divide 3 both sides of the equation, so you see we can get x. Just divide 3. So, and then 3 is canceled. X is 1/3 of y plus 1. Oh, we found it. So that is the inverse function. The inverse function means whenever you give me a y value, I can find the x value. Yeah, that's the inverse. Original function, whenever you give the x value, I can find y value, right? That's the original function. So, but since this is a function, our habit is to use x as the input variable. So we can still use x, just the change of name, because we often use x as the independent variable. So that here in this function, you input whatever the input variable, we call it x. So we change the name. Y, we just simply change, this is the same function, right? X plus 1 over 3, that's the same function, it's only a change of name. So the output, we prefer to use y. So that is our new function, which is the same function, right? They're the same function, except we change the name for the input variable and name for the output variable using our, custom. Yeah, so that is the inverse. Compared to the original function, that is a line, original function, a line with a slope of 3. Now the inverse is also a line with a slope 1/3. So we can draw these two functions. They're both straight lines. And then see the inverse as a function of y, right? X, that's the inverse. But we now change in name. We write the inverse function as a function of x. So you see these two are exactly the same function except a change of name. So that's the same expression. It's only a name for the variable is different. So don't be confused by the look, but look at the form or definition of these functions. They're the same. So now we have this function y in terms of x. And so we can draw this inverse function together with the original function and see their relationship. If you look at the original function, that is y equals 3x minus 1, then that's the slope is 3, negative 1 is y-intercept. So that is a line. This is the original function. But what is the graph of inverse? So inverse, if you have this point is negative 1 because the y-intercept, when x is 0, y is negative 1. And we know what point a negative 1, 0 must be on the inverse. So let's look for where is the negative 1, 0. X is negative 1, y is 0. So this is a negative 1, 0. Also, this must be on the inverse, right? We know if AB is on the original BA, the point must be on the inverse. So let's draw the inverse, and the inverse is a line with slope 1/3. So the slope is also positive by 1/3. So it's a straight line. So straight line passing through that point. So that you can see both the picture of original function and the graph of the inverse. Both are functions in terms of x. So we can see the graphs are symmetric about this line y equals x. Right, so that is a visualization of an invertible function. This is a very special case. The original function is a straight line, so its inverse is very quickly found as another straight line and symmetric with the original function with respect to y equals x. So and once a function is one-to-one, you can use this strategy to try to find the inverse function of a one-to-one function, because one-to-one function is invertible. So then we will look at trigonometric functions, because if you use horizontal line test, they are periodic and they are not one-to-one functions. How do we define inverse? So that's the question we're going to look at.